Hello, I am Matt Eland, and Doctor Who is awesome and bow ties are cool. So, I want to talk to you about two of my favorite things that is Doctor Who and machine learning. And specifically, I'm going to be talking to you about a library in .NET called ML.NET, which lets you do machine learning in C Sharp or F Sharp or VB code.
Let's
So,
see.
if we can apply ML.NET to maybe salvage the ongoing series of Doctor Who. Now, if you're not familiar with Doctor Who is a BBC science fiction series involving a character called the Doctor. The Doctor is played by various actors and actresses over time. So as the Doctor goes on, they eventually will the character will be killed and will regenerate into a new version of himself with a new actor or actress. The Doctor does tend to be a little bit eccentric and typically spends their time trying to save the world with various companions. So that's really what Doctor Who is all about. I am strongly opinionated. I believe the Doctor Who is fairly awesome. This is me at a Renaissance fair as the 11th Doctor with my Fez. That is my favorite of the Doctors. That's somewhat of a minority opinion, but I think it's pretty awesome. And Doctor Who is fairly awesome, or has been historically. It's had some very talented actors, very talented writers, a growing degree of budget has gone into this series to make it better and better over time, and it's been able, at its height, to tackle some really complex and interesting topics in innovative ways, which is really what the best science fiction shows are all about, whether it's Star Trek Next Generation or Doctor Who or Quantum Leap or something else. So I am of the opinion that Doctor Who is awesome or can be awesome. But it is important to highlight that Doctor Who is not mine. Doctor Who is copyrighted by the British Broadcast Corporation, or BBC, and it's run by them. So this talk is really should be looked at more of as an entertainment and educational purposes versus any sort of copyright infringement there. One thing to highlight here is that I will be showing you some machine learning models. Machine learning models are subjective based on the data that they observe, and their opinions may or may not be grounded in reality, because data is just one aspect of the full picture. So I don't want you to look into any of the judgments that the machine learning model that I'll be presenting to you today has made as being objectively real, either in favor of or against any particular actors, actresses, writers, producers, directors, things like that. So this is really oriented to help you understand a little bit more about what machine learning is and what it can do and what insights it might be able to glean. Okay, so with that, Doctor Who has seen some better times. This is a visualization of the various ratings that we've had in Doctor Who over time, and one of the things that you might notice from this chart is that, well, when the series was rebooted back in the early 2000s, it enjoyed fairly good ratings, and those have slowly eroded a little bit. But over the last 5 years or so, they've really eroded significantly. The ratings have been abysmal, and viewership has also dropped significantly. So here are our viewership numbers. Now, a lot of this can be attributed, or is often attributed by fans, to be related to the 13th Doctor, the most recent Doctor, played by Jodie Whittaker. Unfortunately, this is the first female Doctor, which has also engendered some backlash and bias from fans. But you can see that the viewership and the individual ratings of these episodes are not good compared to the rest of the series. And this is similar to a normal show that goes on over the course of its life and then dwindles out in viewership and ratings over time. So Doctor Who is currently in trouble. They've actually really acknowledged that they're in trouble, and they're currently looking at rebooting the series. And so it really is, for the series, it's time to regenerate. So they're going to take on a new Doctor, a new showrunner, and along with it, to go with it, some new content. Since you're putting out new seasons, you got to have some topics of interest. So they have not yet announced who this new Doctor is. I have this lovely article over here from Doctor Who TV on the right. One note about this article before you freak out too much. This was published on April 1st, so I wouldn't take too much stock into Tom Holland as the new Doctor. But someone's going to be the new Doctor, and the show is going to be going off into some new direction. And so this talk is about what can we determine using machine learning as ways of things of recommending to the showrunners and to the new writers for the new series. The way we're going to do this is we're going to go out and train a machine learning model, and we're going to take that trained machine learning model and we are going to give it some sort of a hypothetical new episode, and this machine learning model is going to predict what kind of a rating that new episode might receive. So we'll spend some time training a model. We'll feed it information about a hypothetical episode. Later on, I'm going to show you how I randomly generated a bunch of hypothetical episodes and see what it likes and what it doesn't like. But the process of training a machine learning model is complex. So in order to train a machine learning model, you need to handle that. Handle the training process some sort of data, some sort of data set. So in our case, this is a data set full of ratings for the various TV shows that have occurred in the past for Doctor Who, as well as information about each one of those shows. So in this episode, did it have a Cyberman in it? Did it have Amy Pond in it? Did it have, who wrote it? Those kinds of things. We're giving all sorts of information about the episodes, including what rating they got. That's the label that we're trying to predict. So that labeled data means that we're including the ratings along with the information about the episode. So we're giving all sorts of episodes about new Doctor Who. Next thing you need to do is you need to tell it what type of machine learning algorithm to try, whether that's going to be logistic regression or some sort of a decision tree or something else. But you need to select some sort of algorithm for your machine learning process. For that algorithm, you need to provide hyperparameters. These are really just parameters that modify the performance of that algorithm. So there's some things you need to learn there. You also need to tell a little bit more about how long to spend training the machine learning process. But what this does is it looks at the data set that you're giving it, and it kind of memorizes little patterns that it sees in that data. And it comes up with this trained prediction model. And it spends a lot of time building this model, but once you have the model, it's very quick to make predictions with it. Right? So this is the process of machine learning and making a model. But this is hard to get into, right? So in order to do this, you need to learn a lot about algorithm selection and hyperparameters and what all these means and what the trade-offs between these things are. You also need to figure out, what are you going to be training this model in? Are you going to be using R or Python or SAS or Julia or something else, right? So you have more things you have to learn there. And on top of that, there's even more machine learning frameworks out there. There's scikit-learn, TensorFlow, Theano, PyTorch, Keras, OpenCV. And if you want to deploy all this, you probably are using a web server technology like Flask or something else. And these may not be the technologies that you are working with in a day-to-day basis as a web development team. For example, you might be running a bunch of .NET applications or Java applications, and your skill set is not necessarily in these areas. So there's a lot of new things that you have to learn. Now, Microsoft is awesome, and they get a library for almost anything. And they've given us something called ML.NET, so short for machine learning. And ML.NET is a library that we can use from VB or C# or F# code to train a machine learning model. Okay? So we're no longer having to learn a lot of different things. We're learning one library. We're still having to worry about algorithm selection and hyperparameters. And this is still a decent cognitive load on us that might be a little hard as we're getting into machine learning. So the wonderful folks over at ML.NET have given us a specialized module to help us ease into machine learning a little bit. It's called AutoML. So with AutoML, we are no longer worrying about algorithm selection and hyperparameter tuning. We're just giving it a labeled data set. We're telling it what task we want to do, whether it's regression or classification or clustering or something like that, right? And then we're telling it how long to train for. And AutoML is going to then go in and it's going to try all sorts of different algorithms and hyperparameters and find what works best, what performs the best. So we still have to learn something, but the thing that we're learning is ML.NET AutoML. And it's a very specific, very specialized thing. So it's really shrinking the amount of information that we have to learn as developers to get started with machine learning. So this is why I like ML.NET and AutoML so much. But let's talk a little bit more about what ML.NET is. So it's a .NET library. It works really cross-platform on .NET, because .NET is cross-platform, by the way, using C#, F#, VB, anything that compiles down to .NET code. It's used internally by Microsoft, and Microsoft released it as open source in the spring of 2019. They're continuing to improve it and produce updates to it, and it's both open source and cross-platform. It's a .NET standard library, so you can use it anywhere you can deploy .NET code, whether that's a desktop, mobile, web server, console application. The list goes on. There's so many places you can deploy .NET code nowadays. It's built to be high performance. It performs just as well or better as any major machine learning framework. And it supports something called ONNX, or Open Neural Network Exchange. And this is a way of exchanging models, and you can train a model in ML.NET or TensorFlow, and you can load it in anything else that supports ONNX. So we're now sort of divorcing ourselves between where we are training our machine learning models and where we're deploying them, because they could be different technologies. And this is ONNX, which is also developed by Microsoft. ML.NET is really interesting. It's a really interesting way of working with data. So if we're looking at the training process, we see with ML.NET, we're typically loading data into an iData view. That's just an interface that we use for representing our data. We're then configuring a new machine learning experiment. We are now running that experiment and training a model. Once that model is trained, which can take some time, we are evaluating the performance of that model, and we can save it to a zip file if we want to. We can take that zip file later on and deploy it to a web server and really quickly use our pre-trained models if we like them. We can very quickly create a prediction engine and generate predictions from a trained machine learning model as well. Now, all of this is ML.NET, but AutoML is this bit right here. So instead of having to worry about what machine learning algorithms we're going to be using, we are now trusting AutoML to find the best ones for us. So let's jump in and take a look at the experiment that we're going to be running. Right? So essentially what we're going to be doing is we're going to take episode data with ratings for each episode, pass it into machine learning, which for us is going to be ML.NET's AutoML, and that's going to take some time thinking about it, and it's going to output the best performing model that it finds. It's going to give us a trained prediction model, and we can use that trained model to make predictions about our data. Now, what this is really doing under the hood in this machine learning process right here is it's actually looking over our data. It's looking over all the various episodes, and it's looking at, okay, well, which ones performed well? Which ones have the highest ratings? Which ones have the highest viewerships? And what are the traits of all these individual episodes? What is it that makes a good episode good and a bad episode bad? What do we learn from these episodes? What do we understand from these? And so your machine learning process is trying to really find associations in all this data and internalize it so that it can look at new episodes it's never seen before and make predictions about what ratings they might have in this, right? So it might, for example, say, hey, anything with Rory Williams, we know that's going to tend to be a better episode. Anything with Weeping Angels, yeah, that's going to be a pretty good episode. Anything that has farting aliens, yeah, probably not the best episode. And yes, that was a thing. Check Series 5 if you're, Series 1 if you're interested. That was some of the earliest episodes of Doctor Who, the reboot. Yeah, farting aliens, it's a thing. But anywho, we feed all this data to machine learning, and machine learning comes out and it generates a trained model that we can then combine with some sort of an episode and get a predicted rating for that episode. If we can do this with a bunch of randomized episodes, we can come up with some episodes that we think might be really good for a new season and potentially hand those off to the new showrunners. So in order to do any of this, though, we need that trained, we need that labeled data set. So we need some sort of a labeled data set of Doctor Who episodes with ratings associated with each one. Now, whenever I'm looking for a data set and I don't have one to begin with, I might look at an API or I might look for an open source data set. My favorite place to go for open source data sets is Kaggle.com, which is a free data science community, and they had a Doctor Who data set out there that had a list of episodes. It wasn't quite current. It didn't have all the latest episodes in it, but it had information about who was in each one, who wrote it, who directed it, who produced it, who was the doctor in it, that kind of thing. And it also had information about the viewership and ratings. I had to do some cleanup work, which I'm not going to be stressing too much in this presentation, but I had to get this into a point where I could feed it into my machine learning model. I also gave it everything but the latest episode of Doctor Who, which actually I haven't even seen yet. I'm gonna probably watch that tonight after I record this. But I put all that together, and I was able to generate this merged data set that I could then feed to my machine learning algorithm, or the model training process, and it would be able to find the relationships between the ratings and the individual episodes and the traits about these episodes. Okay, so I took these data sets I got from the internet, combined them all together, and did a little bit of cleaning to get it ready for a machine learning process. It's very normal for machine learning. You're going to need to prepare your data, look for missing values, things like that. One of the things you also want to do is do some data visualization. So you're going to look at your data and see, like, okay, well, what can I spot as a human as trends that a machine learning model might be helped with? Is there a correlation between the given ratings and the doctor that happen to be playing that episode? So we can see that these ones here with the 13th Doctor are not performing very well at all. This particular slide doesn't seem to have the last couple seasons, but the model I did train on did have that. The 12th Doctor, yeah, I mean, some of the poorer performing episodes are maybe worse than many of the seasons before. But we can see that the 11th Doctor performed fairly well. The 10th Doctor steadily got better over time, so you kind of wish that he had a 4th season. That would have been awesome. And the 9th Doctor, pretty consistent, pretty reliable over the one season that he was in. So you can see that, yeah, okay, there is some relationship between the Doctor and the rating or the range of ratings that they're getting. So that might be some information that might be helpful to give to the machine learning algorithm. And you can see, yeah, there is some relationship between the season and the rating and the viewership. There's some various associations. So you're kind of taking a look at the data in various different lenses to see what information might be helpful to provide to the machine learning algorithm, just to help it understand things a little bit more. You can take a look at the distribution of ratings by writer. You can see that some writers had only 1 or 2 episodes, while others had many. Some writers have a very wide range of episode ratings. For example, Russell T Davies had some fairly poor performing ones, but also some of the best ones ever. But in general, he performed fairly well as a writer, and he was a writer for a decent chunk of the series. You can see down here Stephen Moffat performed very, very well as well. Some of the best episodes, in fact, the best episodes, were written by Moffat. But his worst, it was somewhat disappointing as well. Now contrast this with Chris Chibnall, which is who's getting a lot of ire on the internet these days. He's the current showrunner for the 13th Doctor. Those episodes don't tend to be rated as well, and the bad ones are very, very bad, the worst ones the series have ever seen. So you can see there might be some association with writing and the rating that an episode might be given. So that's a good information to provide to the machine learning model. Producer, you can see there's also a range of things as well. Some producers produced a lot of episodes, some of them produced only a few. But you can see that there are some ranges out there. So this is also helpful information. But with all of this, you need to keep things in mind of, well, these writers and producers and directors, they didn't direct throughout the series. Many of them did this for only a year or two, and so they were really strongly tied to a certain doctor, or certain writer, producer, showrunner, even BBC executive. So there is some sort of correlation or association between some of these things. So you got to be careful on this, but this is still useful information for machine learning model to have. Many directors out there. Some of them have directed many. Some of them have directed a few episodes. But you can see that there's definitely an association out there with the directors and the quality of the episodes that they produce. Yeah. So now that you've looked at some of the metrics of these things, you can start to say, okay, well, let's take a look at how we can use AutoML to actually train a machine learning model and get some values for things. So without further ado, let's just jump into the demo. I'm going to show you the application I built in ML.NET. It's a simple .NET Console application, and we'll take a look at how it performs. So Let's just run this application and we'll see it running and work with it there. So first thing, my application is saying, hey, how long do you want to train? How many seconds long do you want to train? From a very small data set like this, 10 seconds is a fairly appropriate time. I might choose 30 seconds. But ML.NET is now going through and it's trying all these different algorithms. And it's trying them and trying to see how they perform, what performs the best. And it's really looping through with different hyperparameters for all of its different algorithms to see what works well and what doesn't. And it runs until it runs out of the time. I told it 30 seconds, so in a little bit here it's going to hit that 30-second marker and it's going to stop. And when it does hit that, it's going to have one algorithm that performs better than anything else, and that's going to be the one that it's going to recommend to me. So it just finished. It told me that the fast forest regression algorithm is the best one it came up with. There are details associated with this. I'm not displaying them to the console, but we could get details about this algorithm. We have some metrics here. We'll talk a little bit more about these metrics in a bit, but this is going to tell me really how well this model is performing. And I can tell you at a glance, this is a fairly average model for this data set. This is performing within half of a rating point. So an episode is going to be giving it a rating between 0 and 10. This is an accuracy of about 0.5 for a given episode. So it's not going to be very exact, but it's going to give you a ballpark of how an episode might be rated. Next thing it's doing is it's actually saving this trained model out to a zip file so we can load it up later on if we wanted to. We'll talk a little bit more about that later on and how you can use a trained model. But now it's asking me how many episodes are going to be in my season. Typically you have 12 episodes in a season, and how many episodes do I want to generate? I'm going to say I want to generate 1 million episodes. So I'm going to hit enter, and it's going to use its trained model to loop through 1 million candidates, get recommendations or ratings for each one of them, and it's going to keep the top 12 episodes. You can see that didn't take very long at all just to evaluate 10 different or a million different ones and find the top 12. And we can see that the best episode involves the 10th, 11th, and the War Doctor, Danny, Donna, Mickey, Nardoyle, and Ood, Osgood, Ryan, and Sarah, facing off against the Daleks, Madame Kavorian, the Judoon, and the Centaurans. We see that this episode takes place in the present and the future, in space. It's not on Earth. It's directed by Paul Wilmshurst and produced by Phil Collinson, who produced many episodes. It's written by Stephen Moffat. Music is by Murray Gold, and it has an expected rating of about 9, give or take 0.5 based on our metrics earlier. So you can see a little bit more details about the individual columns that were present in this data set. And you can see that this episode would get the best ratings by being aired on a Wednesday, apparently. So that's a lot of details there, but that's essentially what we're dealing with this algorithm. We're building this model to predict how well an episode is going to perform, and based on its performance, we're then going in and choosing the best episodes. You can see that episode had a lot of doctors in it, including some who are no longer with us, unfortunately. But it was the best thing of the million randomly generated ones that the model evaluated that it thought would perform the best. Okay, so let's take a look at how this actually works. So here's his actual picture from my wedding day. My poor wife is very patient and had no idea I'd be wearing that hat for that photo. But let's take a look at how this code actually works. First thing you're going to do with a .NET project that you want to use ML.NET on, is you're going to go in and you're going to add some NuGet packages. So we're going to go in, add NuGet packages. We're going to say, hey, I want to add Microsoft.ml and Microsoft.ml.automl. This gives you ML.NET and the automated ML features of things. If you don't want to use automated ML, you don't have to. Automated ML makes it really easy for you to get started with machine learning because you don't have to know the individual algorithms and their performance characteristics and which one to choose when and the hyperparameters for each one and all these things, right? Instead, you're just trusting on it to find the best one for you. So I do recommend you start with these two packages as your dependencies. But let's walk through the individual stages that you'll do as you're getting started. So first thing you need to do is you need to go in and you need to actually load out the data. So we add some using statements for Microsoft ML, AutoML, and data. That covers everything we're doing in these demos, not necessarily everything in this clip here. Next thing we do is we create an ML context. This is really a kind of a facade object that gives you access to all these little facades, such as data and models and all these things. So everything with ML.NET flows through this ML context. So you create one and you work with it. By the way, this new here is a C# 10 ism. This is the same thing as if we had said ML context equals new ML context, just a little bit less verbose. Next thing we're doing is we're going into context.data, and we're saying, hey, I want to load some things from a text file. The type of objects representing each row in this text file is an episode. This is an object that we created. I'll show you that in a second. We're telling it where on disk this is. In my case, this is a CSV file that gets deployed alongside this application. We're telling it the separator character in our file. By default, I think this is a tab. So I'm telling it, hey, this is a comma-separated value file. We're going to use commas. Has header, we're saying, hey, the topmost row of this file is just column names, so don't read that as data. Allow quoting. This is really helpful when you have any sort of cell that might have commas in it that don't represent like breaks between your data. So I will almost always have this on. I will almost always need to turn this on when I'm working with comma-separated value data. Trim white space is just going to chop off extra spaces from the ends of pieces of data. This one doesn't typically matter too much, but I usually leave it on. Okay, so this is going to load an iData view, which is a kind of this lazy evaluated way of looking at your data. So in our case, it's going to load it up from a CSV from the file under data path. The CSV looks like this. This is its view inside of Excel, where we have a header row at the top that tells us what each column represents. And then we have all these little pieces of data, whether it's the title of the episode, or which season it's under, or whether or not the episode was in space, or in the past, or involved the Ninth Doctor, or had Clara in it, or Cyberman, or whatever it might be. Right? So this is just our CSV. It's a lot of these episodes for all the seasons of Doctor Who, which I think it's 13 seasons now, maybe, for the new Doctor Who. Our model file, this is just a plain old C# class, or VB or F# class. The only new thing here is we have this little load column attribute. This load column attribute says, hey, this fourth column into our data set, that's what I want you to map to is special. So in our case, is special here is this guy right here. This is special, by the way. It's just like, is this a Christmas episode, New Year's episode, Halloween? Is this some sort of a different than normal episode? So we can see here the Christmas invasion, that'd be set to true here. So 1 for true, 0 for false. So we do support Boolean columns, we support float columns, we support string columns. We do not support any other types of columns right now in ML.NET. That is something that you're probably going to bump into when you're defining your classes. So keep that in mind. You're usually going to be good to just use bool, string, or float. But you try to do something else, you're going to get errors down the road. This is the most tedious aspect of ML.NET, is creating this class. There are ways of working with ML.NET that will automatically infer this class using dynamic programming and the like, but I do recommend as you're starting out that you actually kind of manually create this class, because it's going to make it a little easier for you to generate predictions later on and work with your data and debug it. And as you move on a little deeper into ML.NET, you can try using those automatically inferred class options that they have. Next thing you need to do, this is actually an optional step, but I strongly recommend it. Next thing you do is you actually split your data. You split your training data, all the data about your episodes. You're splitting it into 2 chunks. 80% of the data is going to be used to actually train your model. So we're going to take 80% of our episodes at random, and we're going to evaluate. The model's going to memorize their characteristics. It's going to understand what's going on in those episodes. It's going to build its model around it. The remaining 20% of the data, we use that to score this trained model. So this model has never seen these 20% of our episodes before. Now, remember, we know the ratings of each one of these episodes in the past because we have rating data from the television data, right? So with this 20% of our data, we're now going in and we're evaluating the model, and we're making predictions from these episodes it's never seen before. So it might choose to say, hey, dinosaurs on the spaceship, we think that's going to be a perfect 10. Spoilers, it's not. It might have actually scored a 7 or an 8 or something like that. And the difference between the actual value and the scored value, we call that error. And that's how we predict how good our model is. That's how we compare one model to another. Is we split our data so it's memorizing all of the training data, and then we check it with this validation process. We do this to avoid something called overfitting. If we just gave all of our data to the training process, our model would memorize all the historical data about Doctor Who, but it wouldn't be very good for predicting new things that weren't related to past episodes. So we try to just take our data, and we usually split it 80-20 or 70-30, some percentage like that, and we use the remaining data just to validate it. We'll talk about a more advanced form of this later on today. But the code for this is just context, data, train, test, split. We give it the data set that we want. This is an iData view. We tell it the percentage that should be kept over for testing. So in our case, 20% goes to validation. So we are taking 0.2 or 20% here. And then sampling key column name, that's a more advanced thing that we don't really need to worry about here. Next thing we do is we configure our experiment. This is a regression experiment. When we're trying to predict a numerical value, that's a regression experiment. I have another video that talks about the various types of experiments you might want to do, but this is a regression experiment, and that tells us a little bit more about the parameters of our experiment. So we tell it how long the experiment should take training its data. This is the value that the user would type in, and we tell it what the most important metric to us is for scoring our models and comparing one model to another. Because they're going to have all sorts of different models and metrics associated with them. So what do we care about the most? In our case, R squared is a pretty good metric to compare regression models with. This is a very average overall metric, so it's a good one to default to unless you have a good case for using a different type of metric. We're not going to get too deep into what these metrics are in this video. Next, we go in and we create a context object, or we create a regression object using context.auto. This is AutoML right here when you see this auto function. We're going to create a regression experiment given these settings. This creates the experiment. It's not running the experiment yet. But our experiment is now ready to be run, and we can go in and perform it. So next thing we do is we call experiment.execute. And this is going to wait for 30 seconds or 10 seconds or whatever the user typed in. And it's going to try all sorts of different things. It's going to take in the training data. You don't have to give it a train test split, but I do recommend doing it this way. We're going to give it the training set and the testing set from our train test data that we created a few slides ago here. So we're taking this data here and we're feeding it into our training process. We're telling it what we want to predict. In our case, we want to predict the rating of each episode. And so with that, we're then saying, hey, go in, spend some time training your model, and when you're done, move on to the next line. So this is synchronous. ML.NET does not currently give us an asynchronous way of creating a machine learning experiment. You might think that's a big deal, but most of the time when you're making these models, performance is not really necessarily the key characteristic. This is not something that an end user is necessarily going to be encountering. You might have maybe a desktop utility where a business person or data scientist is trying to use your code to automatically train a model, in which case you might want to do this on a background worker or something like that. But most of the time you don't care if this is synchronous or asynchronous, because remember, with machine learning, you spend a lot of time up front training your model, and that takes a lot of time. But once you're happy with that model, you put it out into production, and then it's just real quick to generate a prediction from something. So this is an upfront investment. This is not necessarily performance critical, we will say. But it's going to run your experiment. It's going to try all the different automated ML settings it can find. It's going to find a bunch of metrics about the models it tried, and it's going to come back with this experiment result. And we see that this returns a regression metrics result because this is a regression experiment. If this was a classification experiment, we'd get back a classification metrics instead. And we can look at the metrics coming back. We can say, hey, it gives us a whole bunch of things about it. So the best run is telling us, hey, which model did you try that worked the best? Oh, okay. Well, what algorithm was it? In our case, it was a random forest. But then we can get at the validation metrics. So we can take a look at things like the R-squared, the mean absolute error, the mean squared error, the root mean squared error, and the loss function are all things that we have available to us for a regression experiment. For a classification experiment, you're going to have a different set of metrics available to yourself. If you're curious about classification, I have another video talking about using classification in ML.NET to classify or to predict ESRB ratings that a video game might get. So that's a good one to check out as well. But our regression metrics are all measured around error. So our model is going to predict a certain rating, and we'll know the actual historical rating that episode got. And this difference between the two of them, that's our error, right? So all of these metrics here are associated with this error here. But assuming that we like our model and we think that it performs well enough, we can use our model to generate predictions. We do this by creating something called a prediction engine. This is another ML.NET class. This is not related to AutoML. This is used with or without AutoML. But once we have a trained model, we can create a prediction engine from it. This prediction engine takes in an episode, which is again our custom .NET class, and it outputs a regression prediction object. This is a custom .NET class we're going to take a look at in a second. There's really nothing to this class. But we're just calling context.model.createPredictionEngine. And it's going to generate an episode, and it's gonna take in the trained model, which is an I-transformer. So anywhere in ML.NET you see transformer, what that means is it's talking about a model, right? So a model is an I-transformer. So this create prediction engine thing, it takes in an I-transformer. So in this case, it's our best runs model, and it takes in some sort of information about the schema of the data that we're going to get. Schema is usually optional. We happen to have it available to us very easily here because we have train test set, or train set. We have the schema on both, and we can just provide it to there. And that helps it perform a little faster. So in general, if you have a schema, it's good to provide it, but ML.NET is very forgiving if you can't build it one. So this scary 5 lines of code here creates a prediction engine. Doesn't take very long at all. And then we can build any sort of an episode and feed it into the prediction engine, and it's going to be able to output the prediction. And this takes very little time at all. The heavy time investment is training our model, predicting things very quick. Okay, so we're generating a random episode, we're getting a prediction for it, and we're displaying that to the user. Okay, so this regression prediction class is a really simple class. It just has a public float score, right? The naming of this is important. ML.NET looks for something named score. If it doesn't find something named score, it's just not going to set it, and it's not going to work out very well for you. So I do wish that they had given us interfaces or maybe some pre-made classes for us to work with here, so we wouldn't have to bump into these types of things before. But if you're making a regression experiment, honestly, you can just use this class verbatim and you'll be fine. So this takes in an episode that spits out a regression prediction which has a score associated with it. So very easy way of just calling .predict, giving it an episode, getting back an object with a score on it. Easy peasy. So this is a little bit of a tangent, but let's talk a little bit about how we're building these random episodes. I've done a lot of .NET testing in my past lives, and I have used a library called Bogus to help me generate fake testing data. So Bogus lets you quickly generate random data. I'm using Bogus here to generate some data. And in order to do that, I need to provide some rules. So when I'm creating my faker, which is my Bogus instance, I am telling it, like, hey, whenever you see a bool, I want you to give me a random true or false value. Whenever you're looking at the day aired property on a Doctor Who episode, I want you to just give me a random weekday. Whenever you're giving me the title of an episode, just generate a random product name. uh, there is a premium set of movie data that you can buy for, I think, like $10 a year, and you can generate random movie titles there. But this generates a random name with something like legitimate concrete knuckles or something like that. Something fairly random sounding. And then musicians, writers, producers, and directors. We happen to know everybody who's been involved with Doctor Who because we have that in our data set. And it's basically just saying, hey, just pick a random one. Right? So all of this, we're saying, hey, for all these Boolean values, such as, hey, does it have Cyberman in it? Does it have Amy Pond in it? Whatever it might be, just pick a random true or false value. And for all these other ones, pick something that makes sense. So every time we call build a random episode, we are generating a random episode that follows these rules here. So Faker is very good for generating test data, and we're using it here just to generate a whole bunch of data. So when we're generating 1 million episodes, it's just doing this 1 million times. So let's take a look at what's involved in building the perfect episode. So I made a training run. I had it run for, I think, a minute at least last night, and it came up with, I had to evaluate 3 million episodes, and this is the perfect episode it came up with. The title of this episode is Handmade Fresh Pants. It takes place on Earth and in space, in the past and outside of time. It involves Phil Collinson, Rachel Talalay, Stephen Moffat, Murray Gold. It has a rating of 8.65. That actually seems fairly low for some of these ratings that I've seen. But this was the best one that it evaluated. So this model might have been biased towards low ratings. I'm not sure. It featured 10, 11, and 12. So those 3 doctors. It featured the 9th Doctor. Did not feature the 13th Doctor. But it did involve the War Doctor. Who I'm sad that we will never see again. It involved Bill, the Daleks, Donna, the Jadoon, Mickey, an Ood, River, Rory, Rose, Ryan, Sarah, and Sophie. Sophie, if she's not ringing any bells, she appears in The Lodger. So I tried to limit it to companions or characters that show up multiple times in episodes, and Sophie was in several different episodes. And this episode aired on a Monday. Okay, so it is very interesting that it included all the Doctors except for the 13th Doctor. I think it found that the 13th Doctor was a net negative just because her episodes have historically been rated very poorly. So it doesn't surprise me that it avoided the 13th. Remember, this is not making value judgments in episodes, it's making observations from the data it has available. It is using really an all-star cast. I wasn't really familiar with Rachel and her work, but she did Heaven Sent and Hellbent. She did World Enough in Time, the Doctor Falls. These are some of the best episodes of Doctor Who ever made, as far as ratings go. Phil Collinson is just absolutely phenomenal episodes he's been involved. So this is not a shocker that this is our best performing model. Okay? We do see that it takes place on Earth and in space. In general, I didn't see much association here with the settings, but I wanted to see if there was some sort of correlation where episodes in the past suck a little bit more than ones in the present or the future, or whatever it might be. I did actually observe some bias with episodes that are outside of time tended to perform better than episodes that weren't. It's a weird show, so you do have episodes that occur outside of time. And the supporting cast is just fantastic as well, so that's no shocker. But there are some weird things here, right? So Mickey and the Ood are not necessarily very popular characters. Sophie, fairly unusual, and they aired Monday. You wouldn't think that a best performing episode would perform on Monday, but that's when the Runaway Bride showed up, right? So that was a very popular episode, and it's the only one that ever occurred on a Monday. So the model was maybe a little bit biased towards Mondays as a result. So I let it run, and I took all 12 episodes of my perfect season, and you can see here we've got a whole lot of episodes here involving a lot of different doctors, a lot of different opponents, a lot of different companions, but they all are written by Stephen Moffat. They all have music by Murray Gold. Producer and director, it tends to be a little bit more random. Maybe these columns might not have mattered too much to the algorithm. We do see Phil Collinson has done maybe about half of them. But it is interesting that we have just this smorgasbord of opposition and companions and doctors. It's like just throw all of our cast into these episodes was essentially what our machine learning model figured out. We'll talk a little bit more about why it landed on that. So one of the most important things to note about this is that this model really loves David Tennant. It generated 12 episodes, or picked the top 12 episodes, and all 12 of those episodes featured the 10th Doctor. Now, you'll also note that none of those top 12 episodes featured the 13th Doctor. That's because this model undoubtedly associated her with the poor-performing recent seasons of Doctor Who. No surprise there. So, this one loves David Tennant, the 10th Doctor, hates Jodie Whittaker. Sorry, Jodie. We see that the opponents, it tends to rotate opponents fairly evenly. We do see Daleks and Jadoon quite a bit, Zygons and Silent a little bit less so. But it tends to throw in opponents wherever it can. Now, the companions was really interesting to me, because Mickey was the number one companion that it liked. It had Mickey in 8 out of 12 of these episodes. It had an Ood in the cast 3 times. There's some really interesting things going on here. Sophie, which not everybody even remembers, is a very common character. And then you've got Churchill in there, Amy and Jenny. Okay, those are not shockers. Osgood, not necessarily well loved. Ryan can be hit or miss as well. But Mickey was our best one. And I think a lot of this relates to Mickey and just being in some very good episodes early on in Doctor Who, as we'll take a look at later. So, taking a look at what makes a good episode made me wonder, what makes a bad episode? If we wanted to make a really bad episode, what would we do? So, the worst possible episode of Doctor Who that this model was able to generate was something called Intelligent Steel Hat. Again, these are commercial product names. This episode, let's see. This one, it involved the 11th, 12th, and 13th Doctors, as well as the 9th Doctor. Did not involve David Tennant. It did involve the War Doctor, which it surprised me. I didn't expect that we'd see all of these Doctors in this episode. This one also involved Lee Haven Jones and Segun Akinola. There really are only two major composers to Doctor Who, so it did gather that Murray Gold's stuff generally performs better than Segun's, but that's again associated with the 13th Doctor. We had a change in composition. Writer Ed Heim, Ed Heim was responsible for some of the poorest performing episodes, so that's not a surprise. And then I'm not as familiar with Paul Frift. The companions, we're featuring Clara, Danny, Graham, Jackie, Jenny, and Ood again, River, Rose, and Sophie again. We also see Yasmin show up here. So a number of these companions here are associated with the 13th Doctor. So Yaz and Graham, for example, are associated with the 13th Doctor. Clara she showed up as the ratings started to decline before the 13th Doctor came around. And I can't remember a whole lot about Jackie, actually, to be honest with you. I will tell you, I loved Graham. I thought Graham was a fantastic companion. He just came into maybe the wrong era of the show for that character. But yeah, so some of these companions like Yaz and Graham, it's like, okay, well, that's almost like rating the 13th Doctor. It's the same set of episodes, fairly. So if we were to take the top or the bottom 12 episodes of all time, and we were going to put them together into a season, this is what we'd see. We'd see they'd all have the same director and same composition. They'd have a rotating set of writers and producers. Many of these are associated with the newer episodes of Doctor Who. The companions and opposition. Notice the opponents, it tends to have fewer opponents. Companions, we do have a lot of companions still. But let's take a look at the distribution of things. So we do see that 12 out of 12 of those poor performing episodes have the 13th Doctor. Of the rest of the Doctors, the 10th Doctor appears only 4 times. So again, this is a model that loves David Tennant and absolutely hates Jodie Whittaker. Sorry, Jodie. Very good actress. It's just she's not meeting fan desires in this role. As far as the opposition, this one surprised me. 11 out of 12 of those episodes involve the Master. Right? So the Master is a villain who shows up sporadically throughout the series, but as the seasons go on, the Master shows up more and more. Master shows up for the 12th and 13th Doctors quite a bit, actually. So you can see that maybe the Master might be a proxy for what season we're in. And so maybe it might not be related to the performance of the Master, but just the progressing seasons as things go on. We do see that the Jadoon rather never show up in the bottom 12 episodes, and the Weeping Angels only show up once. So this tells us that these two villains tend to perform better than others. But in general, I think the model discovered that adding an opponent to an episode increases its rating. And so we have fewer opponents in these poor episodes than the better performing ones, which tended to have all of them, if that makes sense. We'll talk a little bit more about the experiment setup. Companions, you do see Yaz, Graham, and Rose show up a lot. I was not expecting Rose to show up as much as she did in this list of poor performing episodes. She was a companion very early on in the series for 9's run and a little bit of 10's. And yeah, it surprised me that she showed up in these metrics because those episodes were generally fairly well rated. Mickey shows up a lot here, which surprised me as well because he was he was in our list of popular people. But you can see that Jenny rarely ever shows up at all in a bad episode. So we can see that character does pretty well. But again, many of these characters are proxies for the Doctors or seasons that they occur in because Doctor Who rotates its cast very frequently. Okay, so let's talk about lessons learned here. This model absolutely loves David Tennant. It loves Stephen Moffat. It loves Murray Gold. It loves Mickey, which surprised me. And it loves the Jadoon, which I was not expecting. It hates Jodie Whittaker, which is not a shock to me given the data set that it was trained on. It hates Lee Haven Jones, which was interesting to me. I'm not terribly familiar with which ones he directed. It hates Sagan Ekinola, which is really just a proxy for the latter few seasons. It hates Yaz, Graham, and Rose. It hates the Master. But I was really surprised that Mickey was such a pivotal performer in the good episodes. And so I did some digging. We can see that Mickey shows up early on while the ratings were all fairly good. All of Mickey's episodes were rated above 7. And Mickey avoids some of the worst performing episodes in the seasons that he was in. And he's not in anything, past 2008. So Mickey performs very well, and he's associated with episodes that perform well. It's not necessarily his fault that those episodes perform well. I personally found him to be a little annoying. But it's always good to investigate the findings of your models and see if you can determine any sort of wisdom in those findings. So this is biased data. So there's some things I did wrong in setting this up. Let's talk about some of these things. So ratings are generally going to decline over time, and anything that's going to be a proxy for season, things that show up in the later seasons are going to perform or be penalized more than things that showed up in the earlier seasons while the ratings were still good. Companions are associated with their doctors, as are the staff and writers and directors, all that stuff, right? And then the actual information about the contents of each episode is very limited, right? We only know who's in this episode. Is this in the past? Is this in the future? Who wrote it? Who directed it? Who's the doctor, right? The model doesn't see a whole lot about the themes in the episode and what it's dealing with, and if there's any shocking revelations, or if we are retconning anything, or anything like that, right? Like, the data set doesn't support some of those things, so it's limited in what it can do. There's also a few major characters that didn't show up at all in this data set. So I don't have Strax, who's pictured here, and I don't have Captain Jack Harkness in this data set either. So these are some things that I messed up or were messed up in the data set that I was dealing with, that they didn't get included in the final training data. Also, because I set everything up as a Boolean column of true or false, the model really just tweaked things at random, and it said, oh, well, if I set this to true, my rating is higher. And so it came up with this impossible season of just throwing all of the doctors and all of the companions and all the opponents into an episode, which is maybe not the best way of doing things. If I was going to do this experiment over again, I'd set up our doctor field the same way that I set up our producer or director or writer. I'd have it just be a string value. I might also set up the primary opponent the same way, and maybe add a secondary opponent as well. As we can see, it really likes the Jadoon, it really hates the Suntarans, whatever it might be, right? Having all these extra columns like this also slows down the training process. It makes the training process less effective. It makes you need to train for longer periods of time. So the way I set up my experiment mattered. The data I give my experiment mattered. And this is the result of all those decisions I made as I created my data set. Additionally, randomization is not quite enough for this data set. Since there's so many columns and so many possibilities, just throwing through, getting 3 million predictions is maybe not the best way of doing something. You want either a brute force approach where we're trying every possible combination of things, or you might want to try something like a genetic algorithm where you're basically representing an episode as a sequence of genes, and you're doing things like mutations and crossovers and fitness functions and the like. Genetic algorithms are a little out of the scope of this video, but something like that might be helpful for determining what's a good episode versus a bad episode and having kind of related episodes. So if I was revisiting this experiment in the future, I might choose to do this in order to find a good episode. Additionally, this 80-20 split is not good enough for the data set that we're giving it, because there are only a few writers. Many writers have only done like 3 or 4 episodes. It's going to be very hard for the model to understand that. So let's say there was a writer who wrote for 2 episodes, and both of those episodes show up in the validation data set instead of the training data set. Well, the model's not going to make any associations whatsoever about that writer. So we would need to do things like upsampling. We were repeating rows multiple times to make sure that they show up in the training set and the validation set. That could have helped a little bit. But another thing you could do is something like called k-fold validation. And k-fold validation says, hey, instead of having 2 different groups, a training group and a evaluation group, we're going to have k different groups, where k is some integer. So the first time through, 1/5 of our data set, if we're doing 5-fold validation, so k is 5, we're going to be having 1/5 of our data at random being used for validation, and the rest of it being used for training our model. And the next time we run, a different 5th is used. And we actually do this whole thing k different times, or 5 times in this case. And we average together all the metrics, and that's our score. And this means that all of our data is used for both validation and for training. So our data shows up all over the place. So probably doing this again, I would do some upsampling or duplicating or triplicating or quadruplicating different rows. And I would also use k-fold validation as well. To improve the accuracy of the training process, just to make sure that it's taking all of the data into account. But let's say I really like the model it produced and I want to share it with others. Well, here's what I do. I'm going to save it to disk. I save it out to a zip file, which I'll show you how to do that in a second. I'm going to put it out in a web server, have that web server load our pre-trained model. It's going to create a prediction engine out of it, which again is a very quick operation. And then we're just going to call predict. Right? So training is very slow, predicting is very fast. So here's what that would look like for us. So if we wanted to ship our model, we'd go out there and we'd say, hey, I want to go out there and I want to save our model to this path. I want to call context.model.save. Again, context is our ML context. I'm going to save my model. This just takes in an iTransformer. In this case, it's our best performing model. I'm going to give it the schema. I don't have to give it a schema, but it's good to give it a schema. Again, we have that with our training data set. I'm going to give it a path to a file that we want to save it to. And this one line right here is really all we need to do. And it's going to just serialize it to a zip file. Now, if I have that I can take that zip file, I can add it into a project or download it from a cloud storage or whatever it might be. In this case, I'm just including it in a .NET project. I'm just saying, hey, copy this to the output directory if it's newer than what's present. And that's all I need to do, and my application is kind of bundled with this zip file. Okay? And then when I'm starting up my web server, I can just load that model. I can say context.model.load. I can give it a path to the file, and then it's just going to load up my model. And then I can create a prediction engine out of it like I did before, and then we're all good, right? So we're just calling context model load. This is a really quick operation. It loads it from a zip file, so that zip file that we've included, and then we just have a prediction engine ready to go. And the final application is going to look something really simple like this. So this is a .NET 6 minimal API. This is a single file way of doing it. This could be using a traditional controller and the like, but we're just saying, hey, I want to use my namespace where I define my model. I'm then going to create my experiment. I'm going to load it. It's the method I just showed you. And then, hey, whenever you get a post to this endpoint, this episode's evaluator endpoint, I want to take the episode from the body of that request. I'm going to send it to my predictor called predictor.predict, and I'm going to return a 200 OK response with the prediction. That's it. This right here in .NET 6, this is my web server. This one little file right here, and this is going to serve up my pre-trained model. It's going to spin up pretty quickly, and it's just going to be able to handle whatever request comes in for episodes evaluator, and it's just going to spit out new predictions. Again, very, very quick operation to make predictions, very slow operation to train your model. But you're not training your model on a production web server, you're training it in a utility application or a batch file or something like that, right? Like some sort of an automated process or manual process that you do before you decide to deploy your model. So, can ML.NET save Doctor Who? Well, probably not. Right? I don't think that throwing all this money at Doctor Who in bringing back all of these actors and actresses and villains is necessarily going to be a sustainable business model, especially since not all those actors and actresses are alive anymore. But clearly some change is needed. We look at our metrics here. We see the viewership declining as seasons go on, and the ratings are declining as well. So we see here this is the beginning of the 13th Doctor, and she was given a chance, and those ratings just have not been doing well, or that first season. That second season, they gave her a chance again, and then, yeah, the ratings started declining a little bit more. We had a special. It wasn't an amazing one. And then this last season was actually pretty good. You can see that these dots are getting a little brighter. So the quality is starting to go up a little bit more, but it might be a little too late because the viewership is very, very low. In fact, diehard fans like me, I find it hard to watch Doctor Who because it's never what I hope it's going to be anymore. But there is hope because they are rebooting it very soon. And even if that doesn't work out, and even if Doctor Who dies, which at some point in time it likely will, cancellation is not the end. Remember that Doctor Who was canceled before. And remember how frequently reboot cherished things in future generations. So even if Doctor Who gets canceled, I have firm faith that it will come back at some point in time in the future. But I do think that this model does tell us some things. It tells us that Doctor Who is more than just a set of ingredients. We can't just throw things at something and expect to get good results. You see that the latest seasons of Doctor Who have leaned more heavily on Weeping Angels, thinking that that was the lacking ingredient. It wasn't. It was really the core writing, which is also improved, and the directing and the producing, and the respect that the show is giving its fans and its history. I think that if Doctor Who can remember that it's a show about ideas, it's a show about a show with a history that it needs to respect, and it's all about telling interesting stories in innovative ways, it's going to understand that it's not whether or not something is in an episode that makes an episode good. It's what we're trying to tell, and the respect that we're giving our fans, and the quality of the writing. That's what's going to really make Doctor Who great in the future. And I think it will be great in the future. But, moving away from Doctor Who, how can you get started with ML.NET? Well, first things first, you can start by looking at the code I shared with you here. The description will have a link to that GitHub repository as well as other helpful links. But I suggest that you go out and you try to do a machine learning experiment with ML.NET. So pick some sort of a machine learning task, whether that's regression or classification or clustering or something else. Find a data set or project that's interesting to you. Find some data that supports it, and then go out and try to build it. You're going to get stuck. That's okay. Just Google stuff, look at tutorials, look at other sample code out there. Microsoft has some great samples, which we'll talk about later on. And once you finish it, or you're finished working on it, share your results. This is not a perfect experiment I'm sharing with you here, but it is a helpful one, I find. So AutoML can do a lot of things for you. You can do binary classification or multi-class classification, where we're trying to predict what category something is going to be in. You can do regression, which is what we did here today, where we're predicting a numerical value. You can do recommendation, which is where we're trying to do more of Netflix or Amazon style recommendation. People who like this also happen to like this. And then ranking, which is like, hey, we've got these 5 things. Where would this unknown thing fit into this in terms of ranking order? Is this going to be better? Is this going to be worse? That actually might be very helpful for something like what we're doing here with Doctor Who, finding relative values for our episodes. So as you're starting out, go out to Kaggle.com and find a data set that meets your needs. These are open source data sets. Just do some searching around things that interest you. Do some browsing, see if you find something that's interesting, and then download that data and start working with it. You can take a look at my code. Again, it's all public on my GitHub repository. And again, the description will have links to that. And then you can check out Microsoft's code. If you go to .net/ml, such a hard URL to pronounce, you'll get their website, which has a lot of get started information there. This is open source, so you can actually look through their code and take a look at what works with what. And the documentation for ML.NET is really, really good. It's very task-based as well. So I do recommend you check that out. I obviously produce a lot of videos on data science topics, including ML.NET and Azure machine learning. So give me a like and subscribe if you're curious about more. If you want to find this later on, it's matt.datascience.com. We'll just redirect you to my YouTube channel. If you want to interact with me, ask me questions. Comments here are great, or you can also ping me on Twitter @IntegerMan, which is really a great way of just reaching out and asking questions about machine learning in general, or just catching up on Doctor Who if you want to do that as well. I also write on data science at accessibleai.dev. It tends to be the same content that I put on YouTube, just in article form. And there are some helpful resources out there in terms of books. I really recommend the Hands-on Machine Learning with ML.NET from Pact book, as well as the Programming ML.NET book from Microsoft through Dino and Francesco Esposito. Very good books, both of them. I'm also working on content for an ML.NET course, so if that's something that interests you, follow me on Twitter. Give me a comment here saying that that's interesting to you, and what in particular would be helpful for you. But that's something I want to deliver as my availability allows. Keep in mind I am a master's student, and that can be tough. But I do finally ask, if you build something awesome with this stuff, just tell me about it. I love teaching people. I love seeing what people do with these things that I love. If you learn something new, I'd love to see it. So just reach out, put something in the comments, and I hope to see the awesome things that you build. And I thank you for your time.